So what's up?
What's up is that the fans are in control. It is effectively Mythssion control.
So how does that work?
Cast your mind back to Compact. Remember we smashed two semis into each other at 50 miles per hour, which you said on camera was equivalent to one of them hitting a wall at 100 miles an hour. And the fans went nuts. They are revolting. They rose up and they said, no, two cars hitting each other at 50 miles an hour is not equivalent to one hitting a wall at 100 miles an hour. It's equivalent to one hitting a wall at 50 miles an hour. They say that you were wrong.
Let's test it.
That's what I thought.
It was the episode that had it all. Crashes.
Wow.
Smashes. And according to fans, a subtle physics faux pas.
Both trucks were traveling at about 50 miles an hour when the impact occurred. Now, that's equivalent to a single impact going into a solid wall at 100 miles an hour.
Stop right there. This innocent remark.
Now, that's equivalent to a single impact going into a solid wall at 100 miles an hour.
Sparked a fan frenzy. They reckon that because of Newton's third law, every action has an equal and opposite reaction. The two cars crashing at 50 miles per hour is the same as one car crashing into a wall at just 50 miles per hour and not 100. But can this counterintuitive argument really be right?
Well, if the fans are in control, how do they want us to do it?
Obviously, they want us to smash some full-size cars into each other. But I think we may be able to illuminate some of the physics here with a scale experiment.
Under more controlled circumstances.
Exactly.
And then we get to smash some full-size cars.
Yes, we do.
But first up, Adam is rigging a rig that will replicate the crash in miniature. The part of the car will be played by two weights on a pendulum.
It's going to be loud.
And the wall...
Bring in the immovable object! Bring in the immovable object!
It's time for the immovable object.
will be played by this hunk of steel.
Allow me to demonstrate the rig here. This is our car. It's basically a swinging hammer. This is our wall. It's an unmovable piece of 1,200 pounds of steel. I will be swinging this car into the wall at speed x and speed 2x, which is basically double speed x. That's our 50 mile per hour hit. That's our 100 mile per hour hit. Our measurement will be done simply with a piece of clay that sits right behind the main hammer and between it and a secondary hammer. Obviously, when I swing this car into the wall, that clay will compress. And it will likely compress a different amount at speed x than at speed 2x. And this gives me a beautiful comparison point when I smack two cars into each other a little bit later.
Okay, so the swing from 1x will imitate a 50 mile per hour wall crash, and the 2x swing will double the speed to replicate a crash into a wall at 100 miles per hour.
Car hitting a wall at speed 1x in 3, 2, 1. Satisfying ding, isn't it?
Yeah.
Satisfying maybe, but more importantly, their first data point.
Post-compression length, 1.5.
For a comprehensive result, the guys get into the swing of things and repeat the test 5 more times. Next, it's time to double the speed to 2x for a full swing.
Uncompressed length, 2.6. Car hitting a wall at speed 2x in 3, 2, 1.
I think that's more.
I think that's a lot more.
Yep, and the measurements hammer that home.
0.777. It's a little bit less than twice as compressed as the speed 1x hit.
That makes sense, doesn't it?
It does.
Almost double the compression. But for a larger sample size, they swing into action and repeat the 2x test 5 times. And now that their clay collection is complete...
What's next?
Well, we've got our metric of speed x and speed 2x. Now it's time to smack two cars into each other. So we're going to remove the wall and bring in a second car.
Physicists and fans stand by.
They're identical. Let's do it.
Because this is the moment of truth.
Now, that's equivalent to a single impact going into a solid wall at 100 miles an hour.
Will the clay clear up the controversy, or will it be as clear as mud? In Compact, the fans detected a disturbance in the force.
The airbag went off.
So now it's Mythbusters versus Sir Isaac Newton. But for whom does the bell toll?
These two pieces of clay tell the tale. This is the clay compressed at speed 1x. This is the clay compressed at speed 2x. Now, if Jamie's right that two cars hitting each other at speed x is equivalent to one car hitting a wall at speed 2x, then this is what the clay is going to look like when we smash two cars into each other at speed x. If the myth is true, this is what the clay in those cars is going to look like. Which is it? I quite honestly have no idea.
This is the moment of truth. Are you ready to go? What are you doing back there?
I'm ready. I'm going to cut from top dead center so that the amount of force on both is the same.
Okay.
Here we go. Two cars smashing into each other at speed 1x. And 3, 2, 1.
The clay catastrophe goes under the hammer. And judging by first impressions, it looks like the fans may be onto something.
Well, I'll tell you right now, the compression I can see from here does not look like no 2x speed hit.
It looks like a 1x speed hit.
It looks a lot closer to a 1x than a 2x, but let's do the measurements. 1.54. 1.28.
The results are in. The two-car test clay is almost identical to the clay from the 1x tests, and nothing like the 2x tests.
With all the variance in all of our tests, one thing was really consistent, was that the 2x speed hits looked a lot like this, and the 1x speed hits look a lot like this. And our head-on collision, it looks like this.
So where are we with the story?
Well, the hammers and clay seem to be saying that it's looking pretty good for the myth, that two cars hitting each other at 50 miles an hour might actually be equivalent to one car hitting a wall at 50 miles an hour, and not at 100, as you previously stated.
What do you want to do next?
Next, I want to smash some cars.
All right, then.
Yep, although the impressionable clay supports the fan theory, will that be true when they test the metal of actual automobiles?
Here we are.
At a very special location.
It's a platform 120 feet tall just for dropping stuff. This is a motorized steel barrel just for strapping down a car and turning it upside down. I'm not sure what this one's for, but I'm pretty sure I could come up with something cool to do with it. Where am I? I'm in Arizona, in the middle of 150 acres of pure awesome. This is pretty much what I would design as my ideal playground. It's a test facility designed to break things, smash things, make them fail, and analyze the aftermath. This is one of the test facilities owned by Exponent Systems, and today they're going to help us smash some cars.
And first up to feel the crash force is this.
So this is our car.
This is our car. We're going to smash it at 50 miles an hour into a wall.
Well, let's get started.
All right. How's all this going to go down? This is a 1,280-foot long crash rail. It has a track embedded in it and a cable that pulls a car along that track towards the impact spot. These two V8 engines, which have about 800 horsepower between them, pull this cable, which pulls the car up to the desired speed. When the car gets to about here, the cable's going to release it, so it's traveling only under its own momentum, right into this big steel thing. It's at this point that we'll have a complete picture of what happens to a car when it's going 50 miles an hour and comes to a dead stop by crashing into a wall.
It's not just a picture they'll be getting. Jamie has also added some high-tech trickery to capture the force facts.
There we go. Inside the car, underneath the back seat, is mounted a block of accelerometers that measure deceleration of the impact in 3 separate axes of movement. That information is sent back to a data logger that's mounted in the back of the car. It records all that information. It's kind of like a black box.
This crash, it's basically a data point, one of 2 that we will obtain in order to correctly analyze our head-on collision. Careful viewers will note that in the full scale we're following the same experimental procedure as we did with our hammers and clay. We think it has a nice symmetry. Shall we log the pre-crash length?
Sure.
15 feet.
All right, then.
All right, the cable's ready. Come on in.
With the length logged and the black box engaged, the car is ready to meet its fate, slamming into a solid steel wall at 50 miles per hour.
All right, this is one car into one wall at 50 miles an hour. Take it away.
Okay, Bob, we're ready for off.
The V8 engines roar as they spin the cable. And the car gains speed till it's holding at precisely 50 miles per hour. And then plows headlong into a wall of steel.
Oops.
I hope they're insured.
Yep, it's a car crash, I think.
Yeah, I'd say what happened here is this car here hit this wall. There.
It's a spectacular smash. The force of the impact crunched the front of the car like a car hitting a steel wall at 50 miles per hour, leaving it 3.5 feet shorter.
11 feet 7 inches.
But of course, that's not the only impact stat.
What say we find out what the G load was?
These guys are downloading the data about the crash right now.
Okay, here's the stats on that crash. This car hit that wall at 50.7 miles per hour and took an average of 58 Gs in the longitudinal direction. I'm going to go out on a limb and say that when we smash a car into this wall at 100 miles an hour, the G load is going to be significantly higher.
Well, luckily for us, the only way to confirm that is more car carnage. Adam and Jamie are having a smashing time. All in the name of physics.
How did we get here? Well, it all started when Jamie said this.
Both trucks were traveling at about 50 miles an hour. That's equivalent to a single impact going into a solid wall at 100 miles an hour.
That's pretty sound reasoning for my money, but no, the fans cried. Two cars hitting each other at 50 miles per hour do not equal one car hitting a wall at 100 miles per hour. Because their masses is the same, they cancel each other out, and it's no different than one car hitting a wall at 50 miles an hour. I find this surprising and hard to wrap my head around, but our scale experiments seem to bear it out. But of course, we're not going to leave it there.
This is what happens when you crash a car into a wall at 50 miles an hour. Next up, we're going to be crashing a car into a wall at 100 miles an hour. How bad will it be? We're just going to have to crash it to find out.
So, an identical car, well, except for the fact it's lemon yellow,
That's good. Bring it straight in.
is hooked up to the track.
All right.
Now, the 50-mile-per-hour impact clocked an impressive 58 Gs. But will doubling the speed double the damage to this car?
It's good. I gotta say that after watching that 50-mile-an-hour crash into the wall, I have a really hard time imagining that the 100-mile-per-hour crash is gonna compress the car that much more. I don't know.
So are you ready for some more wanton destruction?
I am! Let's go twice as fast.
All right.
Wanton destruction it is, as the Mythbusters retire to a safe distance and the countdown begins.
You ready to make this happen?
I can't wait. I haven't seen a 100-mile-an-hour crash before.
No. All right, commence with the 100-mile-per-hour crash.
On Adam's command, the engines whir into life, straining to get the car up to exactly 100 miles per hour. It hurtles down the track.
It's going flat out.
The cable uncouples, and the car plows into its final destination. The guys are understandably speechless. That impact crushed the lemon car with such force, it should be in a glass with ice and a cocktail umbrella.
It's in a very different state than it was at 50 miles per hour.
Yeah, it's a little shorter.
I mean, we got a clear difference between the two crashes.
Uh-huh.
I can't wait to see what the data set says about the G load.
If the data's still intact.
If anything's still intact.
Well, thanks to its position in the trunk, the black box survived.
So did we successfully retrieve anything?
We've got good data.
Really?
Yeah, we've got a peak on the left side of 140 and a peak on the right side of 230. And we'd normally just average those to get a resultant there.
So the midpoint's somewhere around 185?
185.
That's nice. That's significantly more than, what was the last one, 58?
58.
Data!
3 times the G's of the 50-mile-per-hour test is certainly significant. But that's not the only data set they're collecting.
Before it was 15 feet. Now it's 8 feet.
So not only did the G-load triple, the crash compacted almost half of the car. And remember, these 2 cars were identical.
This may just seem like some gratuitous violence, but there's actually some really interesting science going on when you compare these 2 impacts. You would think that doubling the speed would give you twice the severity of the impact, but the physics says you're actually looking at more like 4 times the severity of the impact. Our sensors are showing 3 times the G's, and our wreckage is showing about twice the damage. So what's going on here? Well, just like this can, the more I crush it, the more it resists crushing. There's some complex physics going on here, but you don't have to be a rocket scientist to understand it. The cars speak for themselves.
They certainly do. And after 2 spectacular crashes, they have their benchmarks for car carnage.
Well, we've got our data points.
And they are lovely. I guess it's time to move on to the main event.
Yep.
Next up,
Hold on to your socks, Buster.
the Mythbusters think outside the boxing ring.
This car right here hit a wall at 50 miles an hour. This car hit a wall at 100 miles an hour. I think the difference is pretty clear. The question is, when we smack 2 cars together at 50 miles an hour, are they going to look like that? Or are they going to look like this? We're going to smash 2 more cars just to find out.
It's the final act of Carmageddon. 2 cars in a 50-mile-per-hour head-on collision.
Here's how this breaks down. At this end of the track, the yellow car.
And at this end sits the orange car.
And here in the middle, these 2 cars will meet in a 50-mile-per-hour handshake of destruction that will hopefully answer all the questions we have about the crash forces involved.
Adams predicting those answers will give the thumbs up to Newton.
This one has really been a brain bender, but I have a prediction for this final experiment. I think that when all is said and done, it's going to prove that Jamie was wrong and that the fans were actually right. That when these 2 cars hit at 50, they're going to look like the car that hit the wall at 50, not the one that hit the wall at 100.
And Jamie agrees.
Based on our small-scale testing, what we should see at the end of this head-on collision should look pretty much like the 50-mile-an-hour crash against a wall.
It's crunch time for a force impact. Will the full-scale test prove the fans right?
That's it. Well, I think it's time to do the final test. They're all set up.
It would seem so. I'm going to call it. Bring on the head-on collision.
From each end of the 1,280-foot track, the identical 1.5-ton cars take off. Both cars gain speed as they head headlong down the track towards their head-on collision. Then, as both cars reach 50 miles per hour,
It's about to happen.
the cables uncouple.
That was spectacular.
What can you say?
What can you say? That breathtaking finale is the final piece of their physics puzzle. And as the Mythbusters survey the wreck of a 2-car 50-mile-per-hour pileup, they're playing Spot the Difference.
There's a windshield between them.
It's pretty evident, isn't it?
It really is.
It looks just like the 50-mile-an-hour against a wall crash.
And nothing like the 100.
Nope.
Amazing. This tells me the whole story. I don't need to see the accelerometer data or anything. These two cars, which hit each other at 50 miles an hour, look exactly like the car we smacked into the wall at 50 miles an hour. That tells me everything I need to know.
Well, the figures are in. The orange car got 52 Gs. The yellow car got 58 Gs, which, give or take a few Gs, is the same as what we got against a wall at 50 miles an hour.
Gee whiz. And the damage data backs up those numbers. Both of the cars are virtually the same length as the 50-mile-per-hour wall test at 11.5 feet. And after a spectacular spree of automotive mayhem, there is irrefutable proof that those physicist fans had it right. Newton's third law, every action has an equal and opposite reaction, holds true. Although the two-car crash at 50 miles per hour doubles the speed, the energy of the crash is transferred to twice the mass, halving it, resulting in a crash that looks like just one car into a wall at 50 miles per hour.
I made a statement that two cars hitting each other at 50 miles an hour was the same as one car hitting a solid wall at 100. That was a mistake, but you know what? I'm okay with it. That's how you learn stuff.
I love smashing stuff for science.
One way or another, it's all just shrapnel.